I don't know if you've noticed, but I'm not actually Harlan Spence, but I'll be giving his talk. My name is Nathan Schwadron, and I'm giving this talk on behalf of the Crater team. Contributions have come across a very, very productive team. There we are. A quick overview of the instrument. It's really a remarkable instrument. It's basically 3 detectors, each with a thin and a thick portion of the detectors. So detector 1 is the thin portion of the first detector. Detector 3 and 4, again, thin and thick portions, and D5 and D6. These detectors are separated by tissue equivalent plastic, which gives you a characterization of dose, organ doses, lens doses, and so forth. So you get a very good ability to figure out what real doses are like in the lunar environment. You also have the situation in which the deep space, this direction of the sensor points out into deep space, this points towards the moon. So depending on the incidence of particles, whether they're coming from deep space or coming from the moon, you end up with the ability to discriminate between the sources of the particles, which becomes very important for separating those particles that are coming from incident galactic cosmic rays versus albedo particles that are actually coming from the moon. Now, this is a confusogram, but it shows you what we're able to measure and how we separate it out into different species. This is actually the observation that's made by Crater. It's called an LET spectrum. And essentially, it's a unit of flux on the right-hand side, and on the x-axis, you have LET, which is essentially an energy per unit length, or equivalently an energy per unit mass. And these are the energies that are deposited in these various detectors, D1 and D2. Now, this is a little confusing, and I continue to confuse this. When you look at the x-axis, you think in terms of energy. So think high LET, higher energy, and it's actually the opposite. A lower energy particle is going to deposit its energy over a shorter length and will therefore have a higher LET, and the lower LET particles actually consist of the more energetic particles. Now, one of the things that you see, and you really start to see this here when this is modeling from GEONT, you can really separate these LET spectra in terms of various species. This, for example, is the proton peak. You see the alpha peak here. Down here, you start to see the heavy ion contributions. And at this point, the modeling, at least from GEONT, has gotten so sophisticated in HETC heads as well that we really are able to piece apart the different contributions to the LET spectra that we observe on Crater. So when you start to break this down, not only in terms of heavy ions and non-heavy ions, but also in terms of the different species that are contributing, you start to see a very interesting thing. This is the total spectrum, and one of the things that's contributing quite a bit, all of these species are what's called albedo species. For example, in blue are the albedo protons. So these are actually protons that are coming not from deep space, but coming from the moon itself. Their GCR is incident on the moon and generates these energetic particles and come up through the detector. If you ask what that actually, how you differentiate the lunar species from the incident GCR, for example, you can make these plots of D6 versus D4. If you remember, D6 is closer to the lunar surface. So there you're seeing most of the energy dependence is due to the incident GCR, where on D4, most of the energy dependence is coming up from the lunar protons. So if you just segregate these areas in the observations, you can segregate between the incident galactic cosmic rays and the lunar protons. And so we're able to do diagnostics. For example, we can build up a map, a lunar albedo map. This is in a poster that's being presented by Jody Wilson. I encourage you to go take a look at it. It's also going to come out in JGR Planets. But one of the interesting things, when you look at this map, to zeroth order, there's no significant variation that's seen across the lunar surface. So what that's telling you is that depending on different features and so forth, the Maria versus the highlands, you don't see any really major significant differences. But there are some features that have caught people's eye, geologists' eye, and these could be significant. We're going to need more observations to be able to make that point. So we have some to 0th order, no statistically significant variations. Nonetheless, some very interesting features that seem to be showing up here, and we're now clamoring for more counts to be able to see if those really are real. So again, this just makes the same point. If you look at in this case, the yield is the lunar albedo protons divided by the incident GCR protons, and you can see that it really, this ratio is not significantly different depending on different regions on the moon, which is consistent, it turns out, with the modeling from GEON, in which you see that different regions, the Maria, the Highlands, pure ice, each have essentially identical secondary proton yields. That's fundamentally what you're seeing with the albedo, are those secondary protons. So again, a very simple result that seems to be coming out here is that, you know, the moon produces the yield, the fraction of albedo protons divided by the number of incident GCR is relatively independent of portions on the surface. Now, one of the things that we did see as we started to look over time, for example, in the albedo protons, is we started to see some temporal shifts. At first, we thought maybe that was a feature-dependent feature, but in fact, what we realized is that if you look as a function of time, activity has recently started increasing back at the sun, and as a result, the interplanetary magnetic field strengths are actually going up. Now, what happens as the field strengths go up is they become better at shielding the lower energy particles of galactic cosmic rays. So in a sense, the galactic cosmic ray spectrum is becoming hotter. It's becoming weighted towards higher energy particles. So for example, if you take a look at an LET spectrum, the blue shows the spectrum from October of 2009, the red from December of 2010, what you start to see is changes. And remember, the higher LET are the lower energy particles, and so sure enough, you see that those lower energy particles are being shielded out by these interplanetary field strengths. So the LET is actually changing on us. And you can see that here. This is actually some of the first comparisons that we've done between models of galactic cosmic ray doses, that's shown in the red, and actually doses that are observed by the crater instrument. First of all, you see very, very good agreement, and second of all, you see exactly the type of trend that I'm talking about. As those interplanetary field strengths rise, they become better at shielding out galactic cosmic rays, and as a result, the galactic cosmic ray dose drops out. You can actually make a similar plot over a very long period of time. In this case, it goes over much of the space age, and you can see that as you go from solar minimum to solar maximum, in solar minimum, you have weaker fields and therefore higher doses, higher fluxes of galactic cosmic rays. As you go to solar maximum, the heliosphere gets better at shielding these galactic cosmic rays, and so the dose rates go down. And if you take a look up here, we've actually seen the highest dose rates, the highest levels of galactic cosmic rays throughout the entire space age. Now, this recent period of very high fluxes, in this case, these are measurements from ACE showing cosmic ray oxygen. As I said, we've seen some of the highest levels that we've ever seen in the space age. And also, commensurate with that, the lowest magnetic field strengths in the interplanetary medium. Remember, these field strengths are what are shielding out the galactic cosmic rays. And the solar wind pressure, commensurate with that, has also been some of the lowest levels that we've ever seen in the heliosphere. Now, that pressure, this ram pressure in the solar wind, is what inflates the boundaries that separate our entire solar system from the local galactic medium or the local interstellar medium. And so presumably these boundaries are actually shrinking over this period of reduced pressures. That is consistent with observations we've had from the Interstellar Boundary Explorer. So the bottom line is that all of these different properties, galactic cosmic rays, magnetic field strength in the interplanetary medium, pressure in the solar wind, are all linked. Okay, so as the sun starts to finally wake up and presumably is going to do something. Perhaps it's going to go into another solar maximum, although even the solar observers are starting to scratch their head at the depth and the length of this very curious solar minimum. We start to worry more and more about very powerful eruptions, galactic cosmic rays. Excuse me? 2 minutes, thank you. Cosmic rays that are produced by these shocks as they move through the interplanetary medium. This shows some recent modeling of the particles accelerated from these shocks. That's definitely a theme in the solar heliospheric community, is understanding how those particles are accelerated. And in fact, recent modeling from the Earth, Moon, Mars radiation environment model is able to take energetic particles fed in and model them throughout the inner heliosphere, in this case at Mars. This is some comparisons with observations at Mars Odyssey and with Ulysses at 4.9 AU. This was an event back in 2003, a fairly powerful event, a lot more powerful than anything we've seen so far on Crater. But nonetheless, we've developed models that are able to model the rise in solar energetic particles. And sure enough, in June of this year, we saw our first decent event, and we were able to make comparisons between our models. These are from MREM, these are in red and blue, with the observations on Crater. And right out of the box, we got very good agreement. There's essentially no knobs in these models. So the doses that we're seeing are incredibly commensurate with what we're seeing in our models. So a couple of thoughts. First of all, as we start to think about solar activity, we start to think about the various biggest events that we see, ground level enhancements. And in fact, we see evidence of those all the way down into ice cores. These show nitrate concentrations. Nitrates are affected by or thought to be created by solar energetic particles in the atmosphere. And presumably we have records going way back of very, very large events, which shows that these solar energetic particles are really affecting the atmosphere. And that gets to a very large question about the geosphere in general and how it's responding both to the variability of cosmic rays and to the variability in solar energetic particles. And finally, I'll point out that there's a biological connection here, a very important biological connection. If you go all the way back to Darwin's theories of evolution, what you find is he needs a source for a mutagenic source, something that's going to lead to variation in genome and therefore differentiation in species. And cosmic radiation is thought to be one of the leading ideas about how you generate that variation. And so as we start to see changes in the heliosphere, changes in galactic cosmic rays, we really need to be asking questions, that grand challenge about the effects of biology here on our planet and also in planets in other stellar systems and the effects of life there. So in summary, I've described to you the three primary things that Crater observes: galactic cosmic rays, solar energetic particles, and the radiation albedo. All of these effects actually are associated with the term that we've heard earlier, space weathering. These are the effects, there are effects on the moon from these sources. The prime example is the radiation albedo, in which we see the moon really being cooked by this radiation and the radiation coming back to us. And these force questions to us about the changes in our heliosphere and the potential results on the geosphere and the biosphere, the effects for life throughout our solar system and in extrasolar planets, and the effects on planets in general. Thank you.
Trend in the neutron data. So in a session that's in a parallel session, Len also sees this activity as the solar activity increases. The Len neutron flux decreases from the moon.
Yeah, thank you. That's a very good point. Neutrons, we've seen this connection between changes in neutrons and GCR for really throughout the space age. In fact, the neutron monitors on Earth are even used as proxies for what's called the modulation potential. So the fact that there is that connection that we know on LRO is something that's pretty well understood.
Nathan, there was one of your graphs that I found a little bit surprising. It was on the predictions over long time, where you had model predictions from HZ-Tran and HETC heads. Yeah. And there was a separation between those lines that I kind of found surprising, that the models are that divergent. Is there any, now you have, one's a Monte Carlo model and the other is a one-dimensional straight ahead model, but normally under circumstances like this, I'd expect better agreement. Do you have a...
That's a good point. HETC heads, and for the simulations that are showing there, HETC heads was set up with a real model of the whole crater detector. Mm-hmm. In the case of HZ-Tran, we were just running this for a lens dose. So it was a lens dose with 0.22 centimeters squared of aluminum shielding. Mm-hmm. So that's, it's sort of I was surprised at the agreement between those, because it's such an approximation for what we're seeing with for the galactic cosmic ray doses. So really, I think the HETC heads model is a much more accurate description of the device itself.
And so the HZ-Tran was only for